Thanks a lot for the invitation to talk here. So I'm going to speak about a space of rational curve, and let me start by fixing my notation. X for now is a hypersurface in Pn over the field of complex numbers. Of degree d. And for e greater than or equal to 1, R sub Ex is the space of a smooth rational curve. Of degree E on X. And I want to compactify this space, so I do that inside the Kontsevich moduli space. So calligraphic M00xe is the moduli space of a stable map of degree E from arithmetic genus 0 curve of without any marked point. And M bar is the coarse moduli scheme. And of course, Rex is an open subset here. Now, in general, this may be reducible. So if I look at the closure here, it would be the union of a bunch of irreducible components of the space of moduli, of the space of stable maps. So now we want to look at the geometry of these spaces. And I think the original motivation for looking at these spaces was to say something about the hypersurface X itself when X is Fano, in particular something about rationality and unirationality of X. But it turns out that there are some very basic questions about these spaces which are interesting on their own and not so easy to answer. So I'm going to address some of these questions. I'll start with dimension and irreducibility, and then if there will be time at the end, I'll talk about rational curves on these spaces here. Okay, so if we start at, so if we look at Pn, this is a smooth, irreducible of dimension E plus 1 times M plus 1 minus 4. And then we have the universal curve here and the universal map to Pn. And now if I pull back and push forward OPN of D, I get a locally free sheaf here. Of rank D times E plus 1. So this is a globally generated line bundle, and the fibers here are nodal curves of genus 0, and therefore there is no H1. So this is locally free of rank D plus 1. And now if I have a hypersurface here, which is given by F equal to 0, if I pull back and push forward F, I have a section of this vector bundle here, and the 0 locus of the section is exactly the space of a stable map to X. So okay, so the expected dimension of these spaces is or Rex is E plus 1 times M plus 1 minus 4 minus the rank of the vector bundle, which is E times M plus 1 minus D plus M minus 4. Okay, and this shows that the actual dimension is always greater than or equal to the expected dimension, and that if we get the equality, then this is a local complete intersection stack. Okay, and now the question is that when do we get the expected dimension? If we assume that X is general, do we get the expected dimension or not? So this is a natural question to ask. Let me just look at the space of a smooth rational curve. If it, or does it have the expected dimension? X is general, and if it's irreducible, if the expected dimension, if X is general and the expected dimension is positive. Okay, for some cases of this question, so the answer is known. So let me look at the non-Fano case first. So if we have the degree of the hypersurface is large, if D is greater than or equal to 2n minus 2, I think, the expected dimension is always negative. And Clemens, Ein, and Voisin show that indeed there is no rational gap. There is no map from P1 to a general X in this range. If D is between n plus 2 and 2n minus 3, then the expected dimension is negative for all but finitely many values of E. And a weaker statement here, something weaker than the first question, is a conjecture of Claire-Voisin. She asked if on a general X in this range, rational curves have bounded degree. And of course, if D is equal to n plus 1, we are in the Calabi-Yau case, and there is the Clemens conjecture, and probably a similar conjecture in higher dimensions. So this is for the non-Fano case, and now in the Fano case, it is expected that the question has a positive answer. So this is a conjecture I'm going to call conjecture A, which says that assume that X is general. Then the space of rational curves, or more generally a stable map of degree E to X, has the expected dimension for all E. And B, and here, and D less than or equal to n minus 1. And B, that these spaces are irreducible. If D less than or equal to n minus 2. And this conjecture, I think it is attributed, so Harris, Roth, and Starr were the first people who looked at this kind of problems. So I think this is, I'm going to call this conjecture HRS here. And a couple of quick remarks here. First of all, it is important to assume that D less than or equal to n minus 2 here, because if D is equal to n minus 1, there will be always a component here coming from multiple covers of lines. There will be at least two components if D equal to n minus 1 and E greater than or equal to 2. We have always something which is reducible. And the second comment is that here, in both of the cases here, it is important to assume that X is general. For example, for basically any n and d, it is possible to give examples where you get something larger than expected here. So for example, if I look at the Fermat hypersurface, so X Fermat hypersurface of degree d, and I think d should be greater than or equal to 4, then there is a big cone of lines on X. So there is a cone over a base of dimension n minus 3. And one way to get a stable map of degree E is, of course, to have a rational curve, an irrational curve, attached to it, and send this one to the cone and these lines to these lines here. So let me assume that E greater than or equal to 3 to get a stable map. And then if we count the dimension here, that is E times m minus 3 plus the choice of these points on the line up to isomorphism, that is E minus 3. And this is larger than expected, if E is large enough. Okay, so this is always larger than expected, and this also shows that you get something which is reducible. But the thing is that one can answer the same question by looking at the stable maps which are coming from irreducible domains. And that's a different question, and I'll come back to it later. Okay. All right. So let me tell you what is known about this conjecture, conjecture A. So first, if for Harry Frost and a star, let me just write down. Show that A holds for D less than m plus 1 over 2. And I think later George Kuhn and a star showed, among other things, that A holds for D less than m plus 4 over 2, I think, or less than or equal to m plus 4 over 2. And then more recently, Mohan Kumar and I showed that this holds for D less than 2n over 3 and n large. So n large is n greater than or equal to 20 or something like that. And now let me tell you a little bit about so I should also say that these two are basically built on this work here. The same methods and the same approach, but extending the results, basically. And so let me now tell you a little bit about the ideas of the proofs and what can be proved more possibly. Okay, so there is a second conjecture which is much stronger than the first conjecture. I will refer to it as Conjecture B, which says the following. If X is general and D less than or equal to n minus 1, and I think n should be greater than or equal to 4, so then if I look at the space of marked stable maps here, so M01 XE, and the natural evaluation map that we have to X, sending the stable pair CF and P to F of P, there is so if I look at the fiber here, so dimension of the fibers, there is an expected dimension, and the dimension is always greater than or equal to the expected. The expected dimension is E times m plus 1 minus D minus 2. Okay? And the conjecture says that if X is general, then this is always, the fibers are always of the expected dimension. So this is flat of relative dimension E m plus 1 minus D minus 2. Okay, and this is of course immediately implies part A of the conjecture, and this, along with some irreducibility results for small values of E, implies the part B of the conjecture. I'll talk about dimension now, and then I'll come back to irreducibility later. Now the point is that to prove conjecture B, it is enough to prove that it is true for the first few values of E. So if I denote E of X, the integer part of m plus 1 over m plus 1 minus D, then it is not difficult to show that conjecture B holds for all E if and only if it holds for E less than or equal to this number, which I call the threshold degree of X here. And the reason is that if we are, if that one can argue by induction to prove this conjecture, once we know this for the small values of E, now if the degree is larger than this one, it guarantees that if I have any 2 points on X, there is at least a one parameter family of a stable map whose images are passing through these 2 points. And there cannot be a proper one-dimensional such family coming from reducible domains, so there should be maps with reducible domains, and then induction shows that in every fiber that we get here, there is a divisor corresponding to a stable map, which are coming from reducible domains, and then one argues. Okay. So now, if we look at this case here, the threshold degree is equal to 1. So everything boils down to showing that the space of lines through every point of a general hypersurface has the expected dimension, which is n minus d minus 1. Okay? So this is conjecture B for E equal to 1. And now this is a dimension count problem. We know exactly, we can describe the space of lines through any point of a hypersurface easily as the intersection of hypersurfaces of degree 1 to d in Pn minus 1. And now one can, with some work, one can do a basically dimension count and show that this cannot happen for at least one point of a general hypersurface to have something larger than expected. Okay? So this takes care of this range here. I should say that much more is proved here. So there are, corresponding to any graph, we can look at the locus of a stable map with that graph, and then everything, there is an expected dimension, and the expected dimension holds for a general X, and they are all irreducible. So there's more which is proved here. All right, so now if we look at the case of E greater than or equal to 2, the problem is that if we want to describe the fibers of the evaluation map here, it is much more complicated. They are subschemes of weighted projective space, and it seems difficult to carry the same computation that has been done in the case E equal to 1. So we take care of the case of E equal to 2, and this is what we prove. That if n minus 1 is less than n minus d choose 2, then B holds for, conjecture B holds for E equal to 2. And of course, putting all this together, this would imply that conjecture B, if we are in this range, and D less than 2n over 3, so the threshold degree is equal to 2 in this range, or less than or equal to 2, then B holds for every. And that is where the constant comes in the picture to satisfy this inequality here. All right. And everything is, it's possible to generalize to the case of complete intersection. So now if I have in Pn, I have a general complete intersection of type D1 to, say, Dm. And if I let D equal to D1 to Dm, then the same holds here. And so we get that, if we are in this range, we have something which is irreducible of the expected dimension here. All right, so now this is what we have proved, and now we have here work in progress So for this method here, it is not specific to the case of conics. We can generalize it to a higher degree rational curve and therefore generalize the result to higher degree hypersurfaces. And the basic idea is that instead of looking at the fibers of this evaluation map directly and to show that the fibers cannot be larger than expected, we do everything at the level of tangent spaces and at the expense of getting something weaker than we hoped. So basically, the idea is that to replace the stable map with its flag of oscillating planes at that point P, and we replace the space of hypersurfaces, which contain P as a bad point. If P is a point such that the fibers are larger than expected, we look at the locus of all such hypersurfaces, and we replace that by the tangent space inside the big projective space of hypersurfaces there. And then we argue that this thing cannot happen in this range here. So this can be applied to higher degree rational curves, degree 2 to all the way to n, the dimension of the projective space. And therefore, this shows that if the same inequality happens here, n minus 1 less than n minus d choose 2, then we have always something of the expected dimension. So let me just write conjecture B holds here. For all e greater than or equal to 1, all the fibers are of the expected dimension there. And for this we have proved actually, but the work in progress is to apply the method to other examples of Fano hypersurfaces in other projective varieties. So for example, if you look at the case of the Grassmannians, so this is Grassmannian of k-planes in Pn. Then we can do the same thing here. So this is embedded via the Pulukar embedding, and then we can look at the general hypersurface here. I always assume that k is less than or equal to m minus k. This is a general hypersurface of degree d. And then, these spaces are homogeneous, so the space of a stable map, they are smooth, and then the same, there is an expected dimension for the space of a stable map here, which is equal to, maybe I should write it in a different, for the expected dimension of the space of a stable map of degree e to x is, again, e times n plus 1 minus d plus dimension of x minus 1. Okay? And the question is that do we get the expected dimension if x is general? And one can, again, try to argue, like here, try to define this threshold degree and say that, okay, I can prove something like that for a small values of e and then conclude the general result. But the problem is that this number here is huge. So if I look at so again, it is possible to show that the evaluation map is flat when E is equal to 1. And this has been done by a student of Jason. So if D is less than or equal to m minus k minus 1 and x is general, the evaluation map this is 1 is flat of relative dimension n minus d minus 1. Okay? But the problem is that this doesn't really give anything interesting in the case of the Grassmannian. So if, in this case, the threshold degree is equal to the dimension of the Grassmannian, which is k plus 1 times m minus k plus 1 over m plus 1 minus d, I think the integer part here. And if k is greater than or equal to 1, or let's say if k is equal to 1, the threshold degree is equal to 1 only when d is less than or equal to 2. And if k is greater than or equal to 2, there are only very few cases where we get threshold degree is equal to 1. So it is not just knowing the result for lines, it is, we get only very limited cases. But even if we do it for conics, for example, so if I look at the case of lines, say k is equal to 1 again, and if I have d less than n over 3, if I'm not mistaken, then the threshold degree is less than or equal to 2. So it is a much better result if we can do it for conics, which we can do because exactly it is the case of conics that we have done for the case of hypersurfaces in projective space, but with extra work, this case can be taken care of too. So this is something that we can show, and also other higher degree rational curves. So we expect that, but this is not completely finished yet, but we expect that at least when we have, for the case of lines, but it also should be true for higher values of k, that we get an inequality like that here. Let me just not write it here. So that if, again, m minus 1, which should be replaced by dimension of the Grassmannian minus 1 is less than n minus d choose 2, then we expect to get something of the expected dimension if we have a general hypersurface of degree d inside the Grassmannian of k planes, then we expect to get the space of a stable map to x would be of the expected dimension. But it is not completely finished yet. And also, it is possible to apply the same method to other homogeneous varieties, general hypersurfaces in weighted projective spaces, and so on. So there's more work that can be done in this direction here. Okay. Also, as a side corollary that we get from our approach is that we can say something about the space of non-free lines on general hypersurfaces. So let me look at the hypersurface X in Pn. It is again a general, so this is general of degree d and d between 3 and n. Then if you look at the lines on X which are not free, so a space of non-free lines here, it is always of dimension n minus 3, and they sweep out the divisor in X. And the question is that can we get a cone? So can we get a cone? Can they form a cone? And if so, what is the bound and the dimension of the cones of non-free lines that we can get? And this is directly related to the previous problem, because if you have fibers of the, and this can be asked, of course, for other low-degree rational curves, and then if you look at the fibers of the evaluation map, if there are fibers which are larger than expected, there are lots of non-free rational curves which are all passing through one point. So, so the thing is that they can form a cone. For example, when d is equal to 3, I guess as soon as, sorry, when d is equal to 3, as soon as n is greater than or equal to 7, even on a general hypersurface, there will be at least one cone of non-free lines on X. And the question is that can be bounded, and we can give a bound. And so this is the theorem that we can show. If X is general, and P in X is an arbitrary point, and K a number between 1 and d minus 1, then if I look at, for F sub Kp, the space of lines through P with non-free lines with H1 of the normal bundle tensor with minus 1 greater than or equal to K. Then then there is a bound for the dimension of fkp is always less than or equal to the minimum of all positive non-negative a's, such that a plus k plus 2 to k plus 1 is greater than or equal to m minus 1. So there is a bound like this. This is not sharp, but this gives a bound on the dimension of the, and again, similar bounds can be obtained for higher degree rational curves, and they give bounds on the dimension of course, the dimension of the singular loci of the fibers of the evaluation map over there. Okay. So this was for dimension, and let me tell you a little bit about irreducibility and how we can conclude irreducibility knowing conjecture B. Okay. So if I look at any hypersurface X in Pn, say degree less than or equal to n minus 1, and assume that conjecture B holds for X for all the evaluation maps, they are all flat, and also assume that we have the irreducibility of a space of a stable map for the first few values of E. Then Harris, Roth, and Starr show that one can conclude that all of these spaces are irreducible. And the reason is that one can easily degenerate to the boundary and use these two conditions to conclude that what we get is always irreducible here. So the argument very roughly goes like this. If I have this thing here, and if I look at an irreducible component here, then this condition B guarantees that I can always degenerate to a stable map such that the degree of all these, the restriction of F to every component is at most the threshold degree. So there's such thing in the component always, and also that their dimension, the dimension of a locus of a stable map of this form, is of the correct dimension. And then, well, these are irreducible, so one can further basically break these into chains of lines, and that would, with some more work, show that all the chains of lines should be in every component, in every irreducible component. Chains of lines of degree E should be in every reducible component, but you can, there are lots of free lines. Degree is less than or equal to n-1, so there are lots of free lines, and of course, one can find chains of free lines which are singular, which are smooth points of the moduli space here. So, so there should be at most one. There should be exactly one component here. All right. So it is enough to take care of these cases here. And for example, and then again, basically everything goes back to the case of line. So, for example, if I'm in the situation where the threshold degree is equal to 2, and I want to show that the space of lines and the space of stable maps of degree 2, they are irreducible. Okay, so these are the only things to check. And this is, of course, something very classical. The space of lines are always easy to work with. So this is irreducible. And this is irreducible basically because this is irreducible. So if I have a component here, then that component cannot contain only multiple cover, double covers of lines, or union of two lines, basically, because of dimension argument. The dimension of those would be smaller than the dimension of every component here. So every component will have a smooth conics, and therefore it is enough to show that the Hilbert scheme of conics on X is irreducible. So for here, so the irreducibility here implies the irreducibility here if d less than or equal to m-2, so we can make sure there is no bad component here consisting of only double covers of lines or reducible conics. And why are these irreducible? Because so the space of lines are irreducible, therefore the space of double lines in X are also irreducible. And if the space of double lines in X are irreducible, then the space of the Hilbert scheme should be also irreducible. Because if I look at, so let's look at the Hilbert scheme of conics in Pn and the projective space of hypersurfaces of degree d. And the incidence correspondence. Of course, this is a smooth, and the fibers here are projective, they are projective spaces, so this is a smooth and irreducible. So if I have a general point here, a general hypersurface, the fiber is, of course, a smooth, but it should be also connected, because in every fiber we have double lines, and the space of double lines are connected, so it is not possible that the whole thing would be the fiber would be, the general fiber would be disconnected. The whole thing here should be disconnected here. So this implies this one here. So this takes care of the irreducibility of all spaces of stable maps to X when d is less than 2n/3. Okay, so I was much slower than I hoped, but let me tell you now a little bit about a special hypersurfaces. Now, what happens if I have a special hypersurface and we look at the space of a smooth curve on X. So X is a hypersurface of degree d in Pn, and this is just a smooth, not necessarily general. And so what do we know about a space of rational curves on X here? So these are the known results. First of all, if d is very small with respect to n, then it is exponentially small. It is possible to show that the space of stable maps, so M00xe, reducible domain, if there is no line here, this is always irreducible of the expected dimension. And this was apparently proved by Ellenberg and Venkatesh. Okay. If D is equal to 3 and n greater than or equal to 4, then the space of a stable map, the closure, is always irreducible of the expected dimension, and this was proved by Josh, Kuhn, and Star. Bigger than or bigger than equal, I guess. Right? And so what happens if we look at, say, so if D is large with respect to n, we cannot hope this to be true, because even the space of a smooth curve can be larger than expected. So one trivial bound that one can get if D is greater than something like e plus 1 n over 2 times e. Okay, then the space of a smooth rational curve of degree e can be even larger than expected, and therefore reducible. So maybe this is an obvious bound that one can get if one looks at the hypersurfaces here, which contain linear subvarieties of maximal dimension. So thermal hypersurfaces, for example, it might be possible to give better bounds here. But the thing is that it is not very easy to expect what the correct bound for an arbitrary E should be. Even in the case of thermal hypersurface, it is not so easy to find out what the dimension of Rex is. So the only result that I know is that if X is thermal, and if D is roughly less than n over E, then we have always something of the expected dimension. So even there's a stable map of the expected dimension. Expected dimension and irreducible, and this was proved by Matt Deland. Okay, so there is one case that we know, so it's expected that this gives the best bound here, and that is when E is equal to 1. So if E is equal to 1, it is expected that, so the question is that does the space of lines have the expected dimension? If D is less than or equal to n. So it is, so if we look at the first bound that we get over there, the n should be much larger than D. That doesn't give anything interesting here for small values of n, for example. But what we can show is that the answer is yes if D is less than or equal to 8. And the idea is that one can, so if we look at the Calabi-Yau hypersurfaces, we can always get something of larger than expected. So if I look at X in Pn of degree n plus 1, then the expected dimension, so let me call f of x is the space of lines on X, and the expected dimension is n minus 4. But there are many cases that we can have something of dimension n minus 3, thermal hypersurfaces, but there are many more examples. There are interesting examples where you get a big family, an n minus 3 parameter family of lines without forming any cone on X. So it is difficult to geometrically, in an obvious way, classify all Calabi-Yau hypersurfaces with too many lines. But there is one thing that can be done, and that is to look at the map. So assuming that we have something larger than dimension, and say that it's exactly equal to n-3, then we can look at, so this is, say, resolution of singularities, and then the universal curve that we have here, and the natural map that we get to X. And then this gives a map from Hn-1 of X, a map of Hodge structure to Hn-3 here. And one can show that in this range, if d is less than or equal to 8, what we get here, the kernel of this map is a non-zero subhodge structure here. So if I call this one alpha, kernel of alpha is non-trivial. If d is less than or equal to 8. And now if I start from an arbitrary Fano hypersurface of degree at most 8, of course, I can cut it until I get something Calabi-Yau of degree equal to 8. And that would be also something of larger than expected, and therefore a non-trivial subhodge structure here. And one can argue that this cannot happen, that for a general hyperplane section or linear section of a hypersurface, in our situation, you end up getting always something which is which has a non-trivial subhodge structure here. So that takes care of this one here. Okay, how much time do I have? 8 minutes. So I wanted the third part of my talk was to talk about rational curves on the space of rational curves and the uniruledness of these spaces, but it would take much longer than 10 minutes, so I think I just stop here without going through that.
Someone have a question about the last 10 minutes?
Okay, just to clarify, you've solved now the Bar-Dion conjecture for d equals 7 and d equals 8, right? Okay.
And it is, yeah, I mean, it should be, it gives something for an arbitrary d, but unfortunately it is not good enough. It excluded a lot of different cases, but not everything, so.
This isn't a question, but maybe it's a comment that some people, it's a connection that maybe some people haven't made on their own, which is this work on the dimension and irreducibility, these wonderful results of yours. This implies that the genus zero Gromov-Witten invariants in these cases are enumerative. They're actually counting the sorts of things that Schubert and Zeuthen would have recognized, and not an integral over some moduli space with components of the wrong dimension, and who knows what really corresponds to. And as far as I know, these are practically the only cases where we know these genus zero Gromov-Witten invariants are enumerative. There are a few other cases, but this is the bulk of it.
You have your Thanks.